All right, good morning, ladies and gentlemen. This is our first video that we're shooting before class. We'll see how this goes. Okay, so what is friction? You guys did an assignment yesterday that had you, look up in the book the definitions of friction. And so see if you can find it in your notes right now. Flip to the pages, see if you can find it. And we're gonna start off with a lab today. Now that you found your definition. What was that definition? Should have been something like the force that opposes motion. And we are going to start off with a lab. Make something in a notebook that kind of looks like this. We were going to do 3 trials, and they are going to correspond to numbers 3, 4, and 5 on the lab handout that we're doing, true friction. And you guys should have this lab handout on Canvas, so fill it out as we go, as we move along. So the first thing I'm going to do is I'm going to put the block just on the table here. And I am going to use this spring scale. And the spring scale, if you look up real close here, measures force.
Yep.
Right?
In newtons.
In newtons, yes. And so I am going to link it on here. And what we're going to look at is you want to know the maximum force on the spring scale just before it begins to move. Here we go. You got a good angle of that one right there? Okay, ready? Oop.
All right.
Let me start that up. Ready? And
Right when you use the other scale.
we got it mixed up. We're gonna use this one. Okay, so here we go. Here we go. All right, and oh, how come it's more pulling so soon?
That's all right. It's all right. It is what it is.
And, oh, there we go. Oh, okay, 1.2. 1.2.
Yeah, let's call it 1.4, I think.
Okay. All right, so we're gonna write 1.4. Wow, that is really hard to read. That's a 4, ladies and gentlemen. Oh. I should have had my narrow. 0 period started, I think. Okay, so then I'm gonna go ahead and I'm gonna add some what we're gonna call squeezage. And you guys, it might be a good idea if you read through numbers 4 before we do this. So if you haven't done that, read through number 3, read through number 4. And this is a 1 kilogram block. And let me go ahead and switch this out. This is gonna be a little bit more harder to pull here. More force needed. Okay, so here we go. So we're gonna start at 0 and let's go ahead and start pulling. Oh.
That was about 2.8.
2.8, okay. So when we add the block,
and we have a 1 kilogram mass.
This is what the 1 kilogram. And notice that we are recording the maximum force on the scale just before it begins to move. Okay, now we are gonna put a piece of paper underneath. Changing the conditions each time. Okay, and so this is for trial number 3. This is gonna go with number 5. I'm gonna go ahead and here we go.
Whoa, what was that?
I'm at looks like 0.6.
Okay.
Okay. Okay, 0.6 newtons. All right.
What does Newton's third law say about what's going on here, you guys?
Okay, so Newton's third law says that that forces come in pairs, right?
Yep.
And so if we know the force here, if this is the pole force, the force of our pole is this, then our force of friction, which opposes motion, must be the same number, but just with a negative sign in front of it,
Equal in
right?
magnitude, but opposite in direction.
Yes. Okay. So, what is friction? Well, we just played around with friction. And friction, we have the force of the pull. We can figure out what the force of the friction is, right? Just equal in magnitude, opposite in direction. There we go. A little bit of review. Weight is the force of gravity pulling down.
Yep.
Just like the force of gravity, same exact idea here. Represented by mass times gravity. What is the weight of your block?
How can we do that?
Let's go back over here.
Get this out of here.
Let's get it, get rid of that. So here is our block. And how could we measure the weight? Well, I've got these spring scales, right? Can I just measure the weight like this? Oh, too much. Need the brown one.
That spring scale is too weak.
Too weak. We need more strength here. There we go. Right there. Okay, so it looks to be like about 5.4.
5.4 newtons is...
5.4 newtons. Okay, so for the mass of our block here, I don't know this.
The weight.
The weight of our black block here, write down 5.4 newtons. We're gonna need that later. So Miss Moore doesn't forget. Okay. Oh, we wanted to finish up the lab, huh?
Well, let's take a look at the.
What is that question statement number 1? Okay, so it says here is the block being pulled across the table by a horizontal spring or string, whatever. Same idea. Use arrows to represent friction, gravity. Oh, we can do this. Let's do it on the board. Okay, so I've got my block. And then it had, so they use the force of tension. You could also use the force of pull. It doesn't matter, whatever, float your boat. And it wants us to draw in friction, and friction opposes motion. It's going that way, right?
Yeah.
Friction's this way. And it's gonna be, there's some friction. What else? Gravity.
Can't get away from gravity.
It's always there. Gravity's
That which prevents you from dunking the basketball.
and this is also the weight, right?
Yeah.
And then the normal force, which is just equal in magnitude, opposite in direction than the force of gravity.
Yeah.
The force normal, or the force F. Okay. All right. Now it says, now draw a free body diagram of the forces acting on the block.
So how's that going to be different?
How would it be different? Well, it's gonna
You know what? You could erase that block and put a dot in.
It's gonna be exactly the same. So for number, what was it, 2?
Yeah.
The only thing you have to do differently here is, well, free body
You
diagram
could put the
falls
numbers
off.
in.
We could. Wow, that's kind of cute. Okay. What was our weight?
5.4 newtons.
Okay, so that's right here, and we know that's negative 5.4 newtons because it's down.
Yeah.
And then what is our normal force going to be? It's going to be equal magnitude but opposite direction.
Normal force is a force exerted by a surface perpendicular to the surface at that point. And I think you got to go to the next slide before you can justify
Talk
that.
about that one. In a horizontal system, the normal force is equal in magnitude and opposite in direction to the force of gravity. Boom. How much is the normal force acting on your block, on your black block? Well,
Gravity is 5.4 newtons down.
5.4 newtons up for the normal force. Okay, okay. Friction is a force that resists motion.
Well, let's finish putting numbers on this. Here, let's just use that first trial. The pull was 1.4 newtons.
Okay, so I'm going to put 1.4 newtons here.
And if it hasn't moved yet, and that's what we tried to do, is get the maximum just before it moved. And if it hasn't moved, that means that there's no acceleration. That means the net force is 0. That means that the force of friction must be
same but opposite.
Yeah.
And what Mr. Boykin is talking about is the dynamic trinity, which we're going to talk about.
We'll get to that in a
very
minute.
soon today. Okay, but what he said is the block is not moving, right?
Nope, not
so
yet.
It's not accelerating, which means our net force is 0, which means these have to equal each other. These have to equal each other.
Yep.
Okay. So now we are done with 1 and 2 and 3 and 4 and 5. Okay. So friction is a force that resists motion. We know this. There are 2 kinds. Look at my mouse. Okay. We've got static friction. Resist the start of motion. Static means not moving. So static friction is when it resists the start of motion. What was the maximum static friction before your block moved? Well, for our first trial, it was right here.
1.4.
1.4, and then for our second one, it was 2.8, and for our third one, it was 0.6. That's the maximum force of friction, static friction before our block moved. Okay. Kinetic or dynamic friction, which is the sliding friction, resists motion while in motion. So this is while the block is moving, you experience friction.
Yeah.
Right. So different types of friction here. What did the paper do to the force of friction?
Oh, what did the paper do to the force of friction? That was number 3, trial 3. Whoa, that cut it way down.
Yeah, so it made the friction less. Right?
What's going on here?
How much friction depends on 2 things: what kinds of surfaces are in contact, and how tightly these 2 surfaces are squeezed together. Normal force. Okay, and so our 2 trials, we changed both these things. We changed the type of surface that it was in contact with by adding a paper here instead of it being in contact with the table. Contact with the paper, that changed things.
Yep.
And then we increased the squeezage by adding a mass
Right.
to our thing, right? More squeezage, okay? Squeezing together the table and the block, squeeze. And so we changed those things, and we saw that it changed the force that we took to pull. More normal force equals more friction.
Yep.
It makes sense. More squeezage.
Yep.
And for our the one that required the most friction there, that's when we had the block in. It makes sense.
You can see how this works if you rub your hands together. You just rub them lightly,
It's not that bad.
and then you push them together hard.
More force, more normal force, more friction. Hot. Okay. This is important. This is not an equation. It's a proportionality, which means that this is proportional to this. So there's a relationship here.
Yeah.
Let's talk about what that relationship is. The properties of the surfaces determine the coefficient of friction. The properties of the surfaces, because every surface is a little different, right?
Yeah, when we went from the block on the table, we got 2.8 newtons. When we went to the block on the paper, we got 0.6 newtons.
So
that really changed the amount of friction.
This surface is different than this surface.
Yep.
That's what we're seeing. Okay. And well, how can we figure out, what that? We're going to call that the property of the surfaces. The properties of the surfaces determine the coefficient of friction.
And that's the Greek letter mu.
And how do you figure that out? Well, we talked about that there's a relationship between these 2 things. Here is the equation that is actually useful. Mu is equal to the force of friction, this guy, divided by our normal force.
So the normal force stayed the same because that was the weight of the thing when we had the 1 kilogram mass in there. But when we put the paper on, we got a different force of friction for the same normal force that changed the coefficient of friction.
So this is the one that's changing. Okay. Mu.
Sound the kitty makes.
When in doubt, think about the kitty. So this is mu. And do we want to say anything about this? This is the one with no units?
Well,
right?
let's calculate. Let's go back to that previous slide.
Yeah, let's calculate mu for this one.
Yeah.
Okay. So we just said that. I'm missing my black markers over there. Okay. So mu is equal to the force of friction divided by the normal force. What was our force of friction?
Negative 1.4 newtons.
Divided by our normal force, which is
5.4.
newtons. Fixer. Okay, so negative 1.4 divided by, don't you like when the math is easy? And I get negative 0.26, we're gonna call it.
What are the units going to be?
2.6, well, they cancel.
There are no units.
No units.
And in this case, it's negative, but what does negative mean? What does positive or negative mean?
It's just a direction.
So if the coefficient of friction is a relationship between the surfaces that are in contact, does positive or negative have anything to do with it?
No.
So if you got a negative, it doesn't, or a positive, it doesn't make it right or wrong.
If you put a negative positive, you wouldn't get marked right or wrong. There'd be no you wouldn't lose any points. It doesn't matter.
Yeah.
Doesn't matter. Is this 131 there? Let's keep moving here.
Well, on page 130.
Yeah, what's that? Let's go through there.
You have a table of
Oh,
coefficients
yes.
of friction.
Good. Okay, so my finger, I've got a Band-Aid. I was grating carrots the other day and I sliced my finger.
I have a Band-Aid
Oh, we're
too.
matching. And then I sliced my nails. Okay. Okay, so table 6.3, these are typical coefficients of friction. And so rubber on concrete, wood on wood, steel on steel, rubber on wet cement. And what do we see here?
Well, you have mu sub S and mu sub K. What
does
does
it
S and K
stand for?
stand for?
This is mu, the static coefficient of friction,
Yep.
and this is the kinetic coefficient
And
of
notice
friction.
which one is smaller.
Looks like
The sliding friction, the kinetic friction is always going to be less than the others.
yeah. Okay.
Yep. And you can see rubbers are like tires on concrete, and when the road is wet, you have less friction. That's why you have to be more careful.
Oh, that makes sense. Because the friction is what keeps you on the road, right?
Yep.
You lose that friction. Okay. All right, so we have already determined the coefficient of friction, mu, for one of your trials over here. Okay, the negative 0.26. Your homework is to determine the coefficient of friction for the other two trials. Go ahead and begin.
And you have that data right.
All right.
Almost dropped the phone. All right.
Okay.
See you.